Is that working? Oh, there we are. Good. Hey, good morning. Great to see so many folks out here. Great to be back at Surge. I'm Bryan Cantrill. I'm SVP of Engineering at Joyent. I'm here with my colleague, Brendan and Gregg.
G'day.
And Brendan and I have actually worked together many years, and we have actually done for many years what we're going to be talking about today, which is actually debugging real-time systems in production. And historically, Brendan and I have developed real-time systems that are much more confined, much actually simpler than the ones we're seeing today, these data-intensive real-time systems, these DIRT systems. But we've done this for a long time, and we've really focused on latency for a long time. And Brendan and I used to work together at Sun Microsystems. I was at Sun for 14 years before it was invaded by the Nazis. I'm not even going to go on a tangent there. I'm just going to go right on. And so Brendan and I worked together at Sun. We developed the storage product. And we found some very interesting latency issues with that particular product. And indeed, if Brendan is looking vaguely familiar to you, you may actually be recognizing him from a video that we shot years ago when Brendan came running in. Brendan and I were the only ones in the office. Brendan came running in. He's debugging a latency problem. And he says, "You've got to see this." And he runs off. And Brendan, I don't know, I mean, you can look at Brendan. I mean, he's a reasonably athletic guy, but Brendan does not run unless he has to run. If Brendan runs, you run in the same direction that Brendan is running. You don't ask questions. So Brendan takes off, and I take off after him. And we go into the data center. Brendan goes into the data center, and he says, "Check this out." And he props me up, and he shows me something so unbelievable that we had to grab a video camera, and I immediately videoed him doing it again for me right after I'd seen this. So this is Brendan. This is circa 2008.
Hi, I'm Brendan. We're here in the Fishworks lab. Sorry for screaming. It's very loud in here with the air conditioners and servers all around me. We just made an interesting discovery, and we thought we'd show you straight away. So over here I'm measuring disk I/O operations broken down by latency. I've also drilled down to disk I/O operations taking at least 520 milliseconds broken down by disk. This is using dtrace so I can do performance analysis of disks. I'm applying a write workload to 2 JBODs, which are over here. The lights are blinking on these JBODs because they're doing work. What I'm going to do is not recommended. This is not supported. Do not try this at home.
Really slow.
And I can find out that they belong to the JBODs I was just shouting at. So, amazing stuff. This has been made possible by analytics from Fishworks, which lets us look at things we've never seen before. Disk latency, high latency caused by vibration is a real issue. You've seen it. It does exist. Just don't let Brendan shout at your disks. That's right. Don't shout at your JBODs. They don't like it.
So that's Brendan. So the funny thing about this is, so we shot this video. It's over the Christmas holiday. He and I are the only ones in the office. I'm like,
2008.
2008. I'll throw it online, and I know that basically, like, my fellow Surge nerds will check it out. And I figure there are, we'll get like 1,000 views or something like that, and people will like it.
I wasn't even sure you would get 1,000 views. I'm like, will many people really watch this?
Right. Does anyone actually care? As it turns out, we ended up accidentally producing the most viewed content ever produced by Sun Microsystems. And Sun actually had a Super Bowl ad in the late 80s. This has been viewed by over 800,000 people. YouTube is convinced that I'm like some big-time content pimp. So every time I show up to YouTube, they keep wanting me to participate in the revenue sharing program and so on. But the thing that was interesting about this, of course, is that it was a real issue, and it's really actually technically quite deep. And the issues that we're seeing today are taking those real-time issues that we saw in the JBOD and actually expanding them to much sloppier systems. And I talked about this in my keynote 2 years ago at Surge 2010. What we were seeing, and what we were seeing were this new breed of real-time app that was not this kind of well-designed, well-confined system, but this incredibly sloppy, distributed system in which the data, the temporal qualities of the data dictated the correctness of the system. If the data is late, it's wrong. And I dubbed this data-intensive real-time, or DIRT. And so that was in 2010. At Surge 2011, we talked about the importance of debugging latency in 2010. At Surge 2011, my colleague Dave Pacheco and I presented on a dirty system that we had developed, that David developed, that allowed us to actually analyze the latency of a distributed system. And that's an interesting system, and we discovered a lot of interesting things when we did that. But it's somewhat synthetic in nature. And the reason it's synthetic in nature is because that system, it absolutely was a dirty system, but it's not I mean, I hate to use the word, but it's not web scale. It's not internet scale. It doesn't need to just scale right up. But what we're seeing now is that and here we are, SurgeCon 2012, what we are seeing is dirty apps actually becoming increasingly common. If you saw the Vigil presentation, great presentation by Raleigh on Vigil. Vigil's got these properties as well. We're seeing many, many apps that have got these properties, that have got these dirty properties. And the thing that is really accelerating it is the fact that these are mobile applications. So with mobile apps, you're seeing increasingly the human is in the loop. And that has got, that's a mixed blessing. And for us, and one of the things that we're going to talk about today, because it's a real paragon of these new dirty apps, is Voxer. So how many people know about Voxer, have used Voxer? I'm about to do them a huge favor and tell you to download their app. So Voxer is a push-to-talk app. If you remember Nextel back in the day, being able to push-to-talk on your phone, which is a great feature, but of course the telcos took it away because it's great, so we can't have it. So Voxer is an over-the-top app that is a push-to-talk app that effectively replaces SMS and voicemail. So you're talking to your spouse, your friends, or whomever, and it can be many to one or one to many. And the great thing about Voxer is that it's actually a terrific new mode of communication. And indeed, my communication with my wife is basically 100% through Voxer at this point. And I don't say that as a shill for Voxer. I actually wish it weren't, because whenever my wife doesn't respond to my Vox, I'm like, oh, it's down, it's down, it's down. I'm like, I really need you to respond. I'm freaking out over here. I'm like, going and making sure all the servers are up. I really should not be using the services that are actually deployed on Joint. It's not actually good for my mental health. But I can't get off it. It's too addictive. It's a great new way of communication, and it is a canonical dirty app, because with Voxer, latency and scale both matter. And Brendan and I have spent a lot of time, Brendan especially, debugging a ton of latency bubbles, latency issues with Voxer. And I think what we've come to see over the last year is that the kinds of problems that Voxer has had and the way we've tackled them and solved them are typify this new breed of apps. And we're going to see a lot more of this going forward. But just to be clear about what the challenge is, these dirty systems are not like historic real-time systems, maybe safety-critical real-time systems and so on. There is a human in the loop here. A human is at the other end of these systems, generally. Now, that has got good news and bad news. The good news is that when a human is in the loop and you're dealing with human perception, I mean, we deal with things that are tens, hundreds of milliseconds. You cannot physically react to something faster than about 130 milliseconds. So we actually have we've got a built-in delay in our brains, which is very helpful, because milliseconds are much easier to deal with than microseconds when you're dealing with a real-time system. So that's the good news. Here's the bad news. We're these social chimps, and we tell one another about things. And in particular, you can have this really nice designed system that works and is a real-time system, and then, as in Voxer's case, some DJ in Cleveland on their radio show instructs their listeners that they must download this app and use it. And literally, this is what literally happened. Voxer was, no one was really using it a year ago. A DJ in Cleveland, with a very popular radio program, told people to download it. Immediately, they had 30,000 new signups. Within a month, they had 1 million. And that's the network effect. Now, you take a system that you so very carefully designed. Talk about your surge. You've so carefully designed this real-time system, and suddenly, in a month, you've got 1 million people. and the timeliness of the system is the correctness of the system. And if it's not timely, people are going to walk away and never come back again. Boy, is that a challenge. So we really have this kind of dual challenge. We've got the traditional real-time challenge, which historically is really hard systems problems or real-time problems. And we've got this internet scalability problem, also a very hard systems problem, and it's in the same problem. Then, but wait, it gets worse. These are generally over mobile networks. And I don't have to tell you that mobile networks are highly transient in nature. And one of the things that we've seen is that this transience puts a new kind of strain on the system. What it will look like to you and to your app are ill-behaved clients, effectively. Things going away without actually shutting down cleanly. When you have people on a browser, they tend to behave better than people on a phone. People on a browser tend to be on a better network. The network's not transient. You don't go into a tunnel. Now we do all the time, of course. So it makes it a real challenge. What we have seen with Voxer is that all these challenges add up, and it really requires you to understand the entire system. It's not sufficient to just understand your app. You need to understand, and I know it's become a cliche, you truly need to understand the full stack. Now, at Joyent, I think that our kind of core differentiator in the cloud computing space is that we are the cloud computing provider that really believes that the OS matters. That the OS is essential for deploying these new breed of cloud-born apps. So we've got our own operating system, SmartOS, which is a derivative of Illumos, which of course differentiated because it has the TA and BFS commands, is critical commands. I don't think anyone's doing BFS as a service yet, but I think it's an emerging space. But so we have our own OS, which allows us with our own set of tooling, in particular dtrace that I developed along with my Shapiro and Adam Leventhal at Sun, and that Brendan was essentially the first user of, wrote the book on, literally. So we've been using the instrumentation system, dtrace in particular, to really understand that whole stack of software and understand where those latency outliers are coming from, because they can come from many sources. And when Brendan and I were thinking about this, we were trying to collect, all right, let's do a presentation on all the kind of Voxer issues. And we started, and it's like, oh God. You started to assemble the issues, and you realize that, it just goes on for so long. It
would take all day.
It would take all day. And so stuff that we, in fact, we were at a terrific BOF last night with the Riak guys, and we were talking about one of the problems, and like, oh boy, Brendan's probably trying to forget that one. It's like, we don't have the capacity to remember these things at this point. I mean, we've been in trauma for so long. And trauma is, I don't want to put too sharp a point on it, but I think what we've seen is these things up and down the stack. It's not simple. These problems are complicated. We've tried to kind of, for purposes of our explanation today, try to kind of group these into certain areas that we see, not just with Voxer, but with other dirty apps, and the kinds of things that you should be looking for when you've got to go deploy a dirty app. So I think we're going to, we'll hit on application restarts, which is a big one, drop connections, slow disks, boundless memory growth. There's a lot of other stuff as well, but I think we'll start with that, CPU scheduling as well.
And we have a good selection that covers the broad category of topics. So we have CPU, memory, disk network, and in 1 hour you're going to get to see something that's representative of different fault areas.
At this point, you're probably sick of being teased, so enough of the actual foreplay. Let's get on to some dirty disaster porn. I am the Charlie Sheen of disaster porn. I just cannot get enough. Just hoover that right up. All right, so let's talk about application restart. So this might seem obvious, but it's actually critically important. I remember we had one problem where we were seeing high CPU utilization in the app, terrible latency, and the application also is restarting periodically. But we really need to understand this latency problem. And we're like, let's go actually understand that application restart problem. We have designed architectures today to be very resilient with different classes of failure, application failure, and so on. That does not mean, as some would have you believe, that failure is no longer important, that apps can just fail all the time without consequence. Because application failure, even in a highly available or eventually consistent or what have you kind of distributed system that is designed to accommodate that failure, application failure will almost certainly induce latency bubbles. Things will need to reconverge. Clusters will need to reconverge. People will need to gossip to figure out what the hell happened. And they will put the system into a hurdy place. It will survive, and that's the point. The point is to make it survivable. But you will have latency bubbles. If you have an application that is failing, if the app is ever restarting that is always the first thing to go tackle. Make sure that the app is always up first, and then go tackle the other aspects of latency bubbles, because the cascading effects from this, the cascading latency bubbles from application failure, can be so subtle that you're actually better off just making sure the app is always up first, and then dealing with these cascading effects such as they still exist. So, to give you a kind of a concrete example of this, Voxer was running into a kind of a classic issue. Node.js was shitting the bed on econ aborted. So Voxer, like a lot of these dirty apps, uses Node.js as a critical component. Node strings together other components. Node is by no means the only component. We're going to get into these other components in a second. But Node in particular was dying on an econ aborted from accept. So I don't know how many people know this, but this is one of these kind of like, talk about this like the BFS TA track of ancient Unix history, that FreeBSD and the Illumos derivatives can actually return econ aborted on accept, which is a little bit ridiculous if you think about it. That you're having an aborted connection for something that you never actually knew really anything about anyway, other than there was something there. It's like there was a knock at the door and then they were gone. It's like ding dong ditch for applications, I guess. So Linux doesn't do this, and Node.js, not entirely unreasonably, saw an error node that it didn't recognize and barfed. Now the barfing would cause all these cascading effects. Now everybody needs to reconnect. That takes you into the SSL hurdy place. When you go to the SSL hurdy place, that app would often die again. Others would drop out of the cluster. You just get hurdy and hurdy and hurdy. When we actually went and fixed that, which is one of the first things we tackled, we were able to see these other problems and realize how many of the other problems were simply due to the application restart. So again, this is one of those things. It's when you've got an application that is dying, debug it first. One thing that's kind of an interesting footnote on econ aborted. Part of the reason we didn't see it until we really deployed into production with Voxer is, I mean, you think about an econ aborted on an accept, you're really not likely to see that with anyone who's behaving well or over a well-functioning network, right? They are not actually. It's not actually ding dong ditch. It's more like ding dong dead. So you're not going to see that on a well-behaving network. It's part of the reason we saw this so acutely is because people are connecting to it over a transient network. So speaking of transients, let's talk about drop connections. Bryan, you want to?
Sure. And so I wanted to start with a network example to follow on. This is about one of the first things you hit when you scale an application, and I'm sure many of you have run into this, is the TCP backlog. So when connections arrive and you get the SYN packet, the kernel has the ability to queue them, and so the application can catch up. If an application can't keep up with the TCP backlog, SYNs will be dropped. The output I have here is from SmartOS, which is actually very similar to OmniOS. And it has a counter there, TCP listen drop. We've had a whole heap of them, which is bad. The client waits and then retransmits after 1 or 3 seconds, depending on the kernel. And that creates this tremendous latency outliers, which is terrible for dirty apps. The fix for this is, if it's due to a surge, you can increase the TCP backlog. If it's due to sustained load, then you just need more CPU resources. Having a longer queue, but you can't eat it fast enough, the queue will just keep growing.
It's amazing how many people run into that. I mean, you hit a queue length, and people are like, oh, I need to increase the length of the queue. It's like, it does not actually necessarily solve the underlying problem.
Right, it solves one class of the problems, the surges, and that's fine, but not the sustained load. You can try fixing it by increasing the TCP backlog, and if you set the system setting, that might work. If not, then do you need to restart the application so it sucks in the new TCP backlog setting? If that doesn't work, does the application itself set its own backlog length? And so when the application calls listen, it can set its own backlog. So maybe that's the one that's being taken effect, and it's not the system-wide backlog. And also, we're messing around with this value. How close are we to dropping in the first place? How full is the queue, the TCP backlog queue, and how close are we near the end? Can I check this across the cloud for all of my systems so that I know whether I'm tuning? Otherwise, I'm just tuning in the dark. I'm just setting this tunable and hoping for the best. Does any of this sound familiar, the TCP backlog? Did anyone run into this? OK, so I've got several hands up. OK, that's good. Networking 101, just very quickly, just something to mentally visualize it. So my app is eating the accepts, and SYNs go to the tail. We have a maximum length for the backlog. When you hit the end of the tail, you'll drop. And this is the kernel is dropping the packet, and then it's up to the client to retransmit. The kernel code for this is not that difficult. We have TCP input listener. we go and check some kernel tunables. If the number of connections we have is greater than the max, then go and drop. Bump a few counters.
This is even more modern than it used to be, right? It used to just be like, hey, free message.
Right, so this used to actually be much worse. We used to have various points within the kernel was check for some error state for a packet, and if that's happened, free message return. Now, free message gets called all the time by the kernel, and so trying to debug this sort of thing was really complicated because the kernel would just arbitrarily and randomly drop packets, and you had no very easy way to track it down.
I guess this is like a huge difference, I think, between networking people. You and I are not really networking people. Like, they implement the networking stack. This whole idea of, like, you can just, like, drop a packet if you feel uncomfortable. It's so foreign. I mean, you're working on a fix, and they're like, oh, yeah, just free message in that case. It's like some edge condition. Like, what do you mean just, like, I can just free it? Oh, yeah, sure, I'll retransmit. It's like, you people are a little too comfortable over there, I think. Because those retransmits are brutal. And when you're seeing, and Brendan knows, whenever you're seeing those, like, 1 second or 3 second outliers, or roughly around a second, roughly around 3 seconds, you got to go to immediately retransmits. We're dropping packets.
Right, and for the kernel, I mean, you read the code and you see free message return, and it's like, the kernel's like, not my problem. Client can go and retransmit. I can just drop this on the floor. I'm not even going to bump a counter, which is one of the most amazing things of the prior kernel. And so we have gone and cleaned a lot of that up so that anytime the kernel will drop a packet, at least bump a counter, at least go into a function that we can detrace and see that happened. So for this particular case, just to give you an idea of the sort of observability we add to debug it, we can see all the things. So we're looking at when sins arrive, and I'm printing out distribution plots per process. This distribution plot is showing the length of the TCP backlog each time a sin arrives. And on the left, we have CPID for the cached process ID. On the right, it's max queue, which is the current in-effect setting of the TCP backlog. It's something you can't figure out just by running Wireshark on the wire. You need to go into the kernel and say, what is the actual integer value in use? So I can see for 3063, its TCP backlog is 8, which is because the application has overridden it. I can change the system setting all I like, and it's not going to take effect because the application is doing something else. And for the other guy, the actual TCP backlog length is 128. That's the actual in-effect backlog. The histogram shows that most of the time when sins arrive, the backlog is 0, but we actually go down to the 128 plus bucket. We've had 34 sins have arrived in that range, and at the bottom I print the number of dropped packets. So this is just an example of the sort of observability that we found pretty valuable to create for this type of case, because we can then, because it's such a common case for when you're scaling applications, is you'll bump into the TCP backlog, and so we just needed a go-to tool to just run whenever we needed it to find out, are we dropping, how close are we, what is the actual in-effect setting?
Normally it should be said that, so this is a descript here that Brendan's showing you. Normally it should be said that Brendan and I would just demo dtrace live for you, but the reality is Brendan and I don't have the ability to run dtrace together without squabbling over style. Right. If you were at the BOF last night, you can attest to this. Fortunately, Brendan also needs the Dvorak keyboard, which I need to find a way to permanently disable on my laptop. It just locks Brendan out, basically. So anyway, we got to show you the script because we just can't do it without fighting.
And so I wrote all the script, so it is neat. It's in Brendan style, so it's all neat. It might annoy Bryan.
This is what I'm up against. This is why I can't reason with him.
And this one's actually not that complicated. In the kernel code, and it was a block that fit on a slide, there was a function, and then there was a statistic that was incremented. We can just go detrace those two things and then pluck out the bits that are interesting. And so I put that on GitHub, and a different way to present it actually is to, instead of summarizing what's going on, it's to snoop, to trace every single event so you can see it as it happens. And so just another go-to tool I've got is called TCP listen drop, and it will print out a line of output each time you drop, and it will show you the timestamp, the source IP address, port, and so on.
Brendan, where's your annoying starting tracing?
I don't need it to say start tracing. I've got the header line at the top. Haven't you learned my style yet? If it has the header line, I don't need it to say starting tracing.
So easy to troll.
Now, again, just to reiterate, this is the kernel is dropping packets. And so we're able to, if we have this sort of problem, we'll just go and roll a tool and say, tell us, And we don't have to run any special kernel or restart anything. We're using dynamic tracing, we're using dtrace, which Bryan fathered. And we can say, show us those drop packets, just pluck them out. As a project that I won't get into now, I actually wrote a dtrace script that plucked out the drop packets in binary form and then saved them to the Snoop file format, which you can open up in Wireshark. I could also write it in TCP dump. So you can actually, from the kernel, pull the stream of the dropped packets in their entirety and then open them up in Wireshark and inspect them. Just for reference, the code that did the Snoop style drop packets look like that. Ridiculously simple. TCP input listener entry return. It's okay if you don't know dtrace, but it's very valuable to learn. And when we actually do a listen drop and then printfing just the details. A lot of the dtrace scripts I write these days would fit on a slide because it helps me for maintenance and they don't need to be that long. So to summarize the drop connections, I just want to start with this because it is generally a common issue. Drop connections can induce acute latency bubbles, and so we had this with Voxer, where they would have these 1 or 3 second latencies, and it's a real problem for the dirty app. And we needed a go-to tool to quickly analyze it and confirm it. Tunables don't always take effect, and it was invaluable to be able to run that script and check it out. As a second type of issue, this is slow disks. Now, each of these issues that we're going to go through get progressively more complicated. Now, for slow I/O in a cloud computing environment, slow I/O can be caused by multi-tenancy, which is to say neighbors. And you may be quite familiar with this. We have a lot of customers come to us and they're very concerned about neighbors who are running a backup or neighbors who are running a benchmark, which can really hurt. And they're consuming disk resources and it's interfering with your workload. I'm logged into a cloud. I can't see the other neighbor. But my disk I/O looks really bad when I run IOstat, so I'm not sure to what effect that's hurting me. And it makes you think about, what about performance isolation? How are we isolating resources between tenants of the same physical system? So all those sort of thoughts and concerns. Like in the previous example, what we like to do is just go and observe it, find out if it's true, get some data on the issue.
And speaking of it, we actually wrote this slide before. Obviously, we know about EBS, but Brendan and I have never actually used EBS until last night, when thanks to the OmniOS guys got an AMI on AWS, and so we were actually using dtrace on EBS for perhaps the first time. Who knows? Maybe some FreeBSD guys did it. But holy moly! Okay, now I understand what people are so upset about. Like, I get it. I get why you're so uptight about disks. Like, that's not a disk. That's like a tape or something. That's like
right.
Stone tablet. I don't even. And actually, it is very interesting when you're looking at the latency outliers. Very clearly highlighted network congestion. That there's clearly network activity going on. That is because you're seeing those very clear 1, 2, 3 second spikes that indicate drop packets for sure.
Right. I mean, I was concerned when I started seeing the latency because I'm using ZFS, I'm looking at ZFS, and I do a lot of ZFS internal performance, and it's like, oh, what on earth is going on? Like, what have we run into? It's like, oh, we're on EBS. It's someone else's fault. Oh, thank goodness.
Right. So just to be clear, we are only talking about slow disks, not misarchitected storage architectures. So just so people understand that. Sorry to throw EBS on the bus, but quantified it. So
just a nice picture to mentally get us into this space. This is what Unix has looked like for a long time, except for ZFS. So we've got block device interface, which has always been there, VFS, which Sun added in the 80s, and the process will talk to VFS, so it can talk to the file system, block device, and their disks. That box at the bottom should say disks. The word disk fell off. If you're using IOstat, and your IOstat will run at the block device interface, what you're looking at is often asynchronous, and it's really hard to interpret. Especially these days when we have systems with a greater amount of memory cache that's doing write buffering. So the application will write, but the disks will actually do the write sometime later, grouped together. And also we're doing read ahead and all sorts of other things. So interpreting IOstat gets pretty difficult. IOstat also doesn't show you by process ID. What is much easier, well, I did actually solve that problem with dtrace with iosnoop, which if you have a MacBook in your room, you can do sudo iosnoop, and you're running a dtrace-based tool that I wrote that will trace disk I/O, which fortunately they ship with Mac OS X. That's happening at that layer. Higher up, if we trace there, we're in synchronous context with the process, and that's really good in terms of latency because the latency that we measure is equal to the blocking latency for the process, and so it becomes very easy to interpret. Interpreting IO-stack gets tricky. IO-stack can be asynchronous, but if I'm measuring it high up, that's what matters.
And there's an important point here, Bryan, for a second, because even if you are on a putatively event-oriented asynchronous system like Node, like Nginx, like any of these event-driven systems, your I/O to the spindles is always synchronous. Now, in Node's case, it's happening in a thread pool that you can't see. But because it is always synchronous, that thread pool can get corked. So this is an example of where you actually need to be aware of how the system is built. It's not just all async happy magic. There's some serious sadness over here, and that has to happen. Now, for our purposes in terms of observing it, it's actually helpful to have it be synchronous because we can actually go determine what the latency truly is.
Right. Now, since we have IO-stack down at that level, let's have IO-stack up at the VFS level, and just to show that it's very doable, it's just some kernel work. Bill Pievsky from Giant wrote a tool called VFS-stat. VFS-stat is modeled on IO-stat, but it's at the VFS level. And that's much easier to interpret because you can say any latency shown here was suffered by my applications. I don't need to worry about asynchronous or synchronous. What I wanted to show you, however, was my go-to tool for doing this sort of thing on the cloud, and that's a tool I wrote called zfsslower.d. That takes a millisecond argument, and it shows, it will only print out I/O that is slower than that value. So I've run ZFS slower space 10, which is what I normally do if I'm on the Giant cloud. ZFS slower space 10, show me the I/O that is slower than 10 milliseconds, and then it will show me the process, the time, some details about the I/O, including the path name, just to confirm if the problem exists in the first place. Because a lot of the time the customer says, the disks look bad, we're running some sort of monitoring, it's looking at IO-stat-based metrics. Therefore, my application's slowness is caused by the disks. And this lets me confirm it much more accurately. I'm doing it in synchronous context. And if the I/O is really fast, it's not the disks. Maybe you're doing too much I/O. Maybe it's just the quantity of I/O. But I can immediately identify if there is high cases of outliers. So I say most of the time, maybe like over 90% of the time, I run this and I don't find anything, and then I find out where the real issue is, which is very helpful. It's helpful to have tools that identify where a problem is not, because we can then focus resources on where the problem is. Last night, I was in the bath with Basho, and this is when we're on the AWS instance, and it was amazing. I run ZFS slower, and it's like, oh, 10 milliseconds? I need 100 milliseconds. It ended up running it with 1,000 milliseconds, and we were looking at the over 1,000 millisecond I/O that were happening, which is probably the longest I've run it with. So go-to tool, very useful, very easy to do. It's written using dtrace. I'm tracing inside the kernel. I'm looking at ZFS read and write kernel functions, recording a timestamp on entry, recording some details. On the return to those functions, because since they're in synchronous context, I can just do a delta and then print out the slower issues. And I first wrote this for the dtrace book, and I'm now using, like I said, it's a go-to tool. I use this all the time to early on identify, and you're basically taking the kernel stack, and I'm drawing a line at VFS, and I'm saying, is the latency below this line or above this line? And if it is below this line, I can then go into ZFS, and I can go to the block device interface and narrow down where that latency is. But if it's not, that's really helpful as well, because we can focus our analysis elsewhere. To show what the kernel looks like, we're fortunate in SmartOS because there's a nice, neat interface between VFS and the file system. And so there are, for all of the POSIX calls, we have functions we can go and trace. I did this recently on Linux for ext4, using one of the prototype dtrace versions for Linux. And
why not system tap, Brendan? Just kidding.
You're trolling. You're trolling. Why not system tap? I did write a blog post on system tap. System tap is hard to use. In fact, the prototype version of dtrace is easier to use and less fragile, although still fragile. And I found this wasn't actually as easy inside ext. They didn't have as clean an interface. Still doable, just a bit more work. So ZFS slower.d is tracing at the VFS interface. IO Snoop, in case you've run that before, and I see a lot of MacBooks in the room, so you can run it on your MacBook, that's tracing at the block device interface. If you run both in Windows side by side, you can correlate. And so let's say in the few cases which happen, we do have slow I.O. that ZFS slower.d has identified. So we've got a 1,000 millisecond I.O. Okay. We can then go to IO Snoop, and from the block device interface, is that slow I.O. originating from the disks? Now, if it's in both areas, I can go down into the disk itself and figure it out that way. If IO Snoop is fast, but ZFS slower is slow, we know that the latency is coming from the file system, which can happen for all sorts of different reasons. File systems lock, and they do transaction group flushes, and they do resilvering, and there's a huge category of issues that can originate from the file system. In fact, if you're using IOStat to look at your block device interface, this actually may be painting a rosier picture of your performance because you have issues that originate from the file system that you can't see at the disk level. So by looking at both, we have the full story, and we can also narrow down the location of latency. So correlating the latency layers was really useful. You can actually write a complicated dtrace script that does the same thing, that will narrow down the latency layers. I can write a dtrace script that in one script does node.js tracing, VFS tracing, ZFS tracing, block device tracing, device driver tracing. I could go into the SAS driver or the MPT driver, whatever, all in one script. I just wouldn't want to maintain it because it'd be really long and complicated. I like writing smaller scripts and you run them separately, just based on years of experience of doing this. If it's text-based, that's fine for slow I.O., like we saw yesterday with the 2-second I.O. If you have high-frequency I.O., trying to correlate thousands of pages of text is a bit hard to do. And so that's why we do heat maps. And this is an example heat map. Now, this is something that Bryan and I created. I guess we started in 2007. We shipped it in 2008. And we're the first people to take latency and present it as a heat map. And we did that as part of a ZFS appliance. And since then, it's appeared in other places. I've seen it in Serconis. I've seen it in Tracealytics. It's really useful. What it does is, but one of the problems with heat maps, however, is it's new and it's different. And so people don't have like looking at a line graph, it may not be as intuitive. And so the quick rundown on what it does, on the y-axis we have latency. On the x-axis you have passage of time. Think of, if I looked at my events, these events, all of the events, and I was to print the latency and the time as a scatter plot, that would be pretty interesting because I'd get to see the full distribution of latency over time. Scatter plots aren't practical at scale because you can be doing hundreds of thousands of I.O. on distributed systems, and a scatter plot means you have to record the x, y coordinates for each. And if you want to do this in real time for real-time observability, that doesn't really work. But heat maps solve that problem because we quantize the latency into buckets, which are these nice big pixels, like in an Atari 2600 or Commodore 64. And so since zero latency is at the bottom, and then the latency goes up for the heat map, each pixel is colored based on how many I.O. fell into that time and latency range. The darker the color, or the greater the saturation, the more I.O. were there. So this particular heat map is pretty crazy. It's on the bottom axis. We see there's a lot of fast I.O. This is just an example. It's system calls decomposed by latency and system call, and I've highlighted read syscalls. So most of them are fast, but then you can see that there's this pattern where some of these I.O.s are slower. And picture if, and this is why we did this, picture if instead of looking at a heat map, we were to do an average latency per second. What you do is you take that vertical information and squeeze it into a line, and if you're just looking at a line, you don't know that this is actually reality, that we have different modes of latency have occurred. That happens pretty often in real life because you have a fast path and a slow path to some system. or you have cache hits and cache misses. So very frequently you do have the fast latency and the slow latency. And each time I see people squeezing into a line, it's problematic. And also, if you just look at a line, you might assume that you've got a Gaussian or a normal distribution, when in fact, this is not a normal distribution. This is something else entirely.
I don't know what Atari 2600 game this is. It's like Defender on the worst possible level. I'm not sure. Yar's Revenge? I don't know. I'm not sure.
Yeah, it's Moonlander. You're supposed to land over there.
This is Brendan's true talent, is the ability to look at a heat map and identify the Atari 2600 game that most closely corresponds to it.
And then, I should have a slide deck just on that. You're teasing me.
So easy.
So, I actually don't understand the reason for this. I just threw this in. This is something new that I discovered. We're all often discovering new things that are pretty crazy, but also very illustrative of what's really happening that we didn't know about because we didn't have the information. Here's a real latency heat map for the disk I/O, and I confirmed with Bryan before we gave this talk. It's like I can really show like all the really bad disasters that we've had.
Oh yeah. Oh yeah.
And Bryan's like, yes, it's
Wow,
surge.
that's a skid mark. Oh yeah. Sniff it.
So Bryan said it's appropriate for this audience. It's surge. It's disaster porn. So this shows we've got logical file system operations decomposed by latency and server host name for ZFS. This is so ZFS I/O. Most of it's fast, but there are these little spots that might be hard to see. We call them latency outliers. And the y-axis scale goes up to 5 seconds.
After having denigrated EBS.
That's right. Yeah, forget what I said about EBS.
Multi-second I/O. We've never seen that.
Wait a minute. Did that slide
our own
deck?
cloud. Oh, shit, God.
Why did I put this slide in here? This is why I asked you. Okay, so the latency right at the bottom is good. Then you have bad latency, and then like very bad latency, in the hundreds of milliseconds. And like to have I/O that's in the 3 to 4 second range, this doesn't even make sense. This is inconceivable. There's a problem with my script, surely.
Surely.
Surely it's fast.
Now, it should be said that we deliberately colored this to highlight outliers. So, I mean, the number of I/Os you're seeing are 1/10,000th, 1/100,000th of the I/Os. But when 1/100,000th of your I/Os take 5 seconds, that's a huge problem. That's an inconceivable problem.
And averaging them, you do lose the outliers because they become such a small fraction. And so the heat map is excellent at identifying the outliers. And these are the ones that cause problems in these dirty apps. So inconceivably bad, 1,000+ millisecond VFS level latency. There's a bunch of reasons why it can happen. In ZFS, it groups together writes and then we'll flush them out. That's a ZFS sparse sync. We've been tuning them to reduce that factor. Other tenants benchmarking can. The worst case of multi-tenant performance is when someone does a benchmark. Because the point of the benchmark is to drive the system to its limits, and that does hurt neighbors. And so we added, a while ago, we added I/O throttling so that we could have performance isolation between tenants in ZFS. And so now this is not so much of a problem. Reads queuing behind writes, and I've got a scatter plot when I was actually debugging this in detail. I took the output of IO Snoop and then plotted, this is when the heat map isn't quite enough and I actually need the per IO information. And so I was doing reads in red and writes in blue to look for correlations and discovered that on the LSI perk card, the reads were queuing behind writes for a very long time. And so I was able to this is a horrible issue.
You may remember the perk from such surge talks as, is anyone else seeing the same multi-bit ECC errors that we're seeing? And why does my perk keep disappearing? We're ripping the perk out, but perk versus EBS fight. This is another reason why hardware rate controllers are a terrible idea. You just can't see what's going on.
So that was great to do, and I was able to bring those latencies right down with some perk tuning. And we can do deeper analysis as where needed. This just shows a stack backtrace when we're doing block device I/O from dtrace. It's a very simple one-liner. But you can picture any layer of the kernel stack backtrace I can go and write a script for to get more information as needed to really drill down. We don't have, in our environment, we don't have these sort of long-term file system or disk issues that are unsolved for months because we just go solve it, because we can just go and write the observability into the kernel as needed. So to summarize that, it's usually not the disks or the file system. We can rule that out quickly, usually. I mean, we've had those issues, so we've experienced the pain. Some of the times it is. Some of the times it's due to big I/O. I was reminded of this last night at the BOF. One time I was looking at I/O and it looked like there was disk reads. It was over 10 milliseconds, and yet the disks were completely idle. And as it turns out, it was because of large I/O. If you actually do 30 or 40 megabyte reads, even though you're coming from cache, just the time to do the copy from kernel space to user space can start to add up. So you may still have, if you have big latency in the joint cloud right now, check the size. If you're doing 100 megabyte I/O, maybe it's just because it's copying it from kernel to user.
So we got limited time here, but we're going to zing through memory. So you want to?
Sure. So for memory growth, just as the next type of issue, Riak had endless memory growth. We expected 9 gigabytes, but after 2 days, the RSS was 40 gigabytes, and it kept growing. And they had to restart Riak to work around this issue. So if you looked into the heap and used, say pmap, you had just binary data. It's what's actually in the heap and why are we endlessly growing. Maybe a problem that you've experienced a lot. Is it a memory leak in the first place? I mean, a leak is where the application or something's forgetting about data and it can't clean it up. Is it in the app logic, Voxer? Is it in the database logic, Riak? Is it in the database's Erlang virtual machine? Is it in the operating system libraries? Is it in the operating system kernel? Or is it just plain old application growth? Your application's growing because it's storing more stuff. It's been up for a long time.
There's like a dude that died who had a lot of enemies. It's like, boy, you got a long suspect list. This could be anybody.
So, yeah, I mean, think about where would you guess that the issue was. And Voxer, they looked at it and they didn't think it was them. The Basher guys had looked at it and they didn't think it was them. And then it came to me, and it's like, is there a leak in the OS that's causing our app to grow? And it kind of didn't seem likely, but at least I can check. I can go and look at the library and kernel allocation. As it happens, we're using this thing called libumem for allocations. It's fast, scalable object caching. It's a userland version of kmem, a slab allocator. I began by trying fixes by experimentation, so setting the backend to be mmap instead. That wasn't working. And then detailed observability can be enabled to find out exactly what the allocator is doing. And there's various outputs that look like this. So umem malloc info, so we can really drill down into the allocator. Takes a lot of time though, looking at different areas in memory. This particular one we had, the break pointer was very high. But the actual memory in use was low. And once we saw this, we started thinking, maybe there's a problem in the OS library, because this shouldn't really happen. I mean, the only scenario this would happen is if the application did, say, a 5 gigabyte alloc and then freed it, and as a consequence, pushed the break pointer for the heap out, and then that came back down again. As we know, like for most operating systems, when you free inside the application, it doesn't actually free. It doesn't give that memory back to the operating system. The library keeps hold of it so that it can reuse. And here, the library was keeping hold of 5 gigabytes and change, and I was just trying to rationalize, why would the library do that? And it was growing. So using dtrace to look at the actual requested malloc size would quickly identify if we had these 5 gigabyte mallocs that were causing the break pointer to move out and that would cause the memory growth. This is a very simple dtrace one-liner. We're looking at malloc entry. These are the size of the memory allocates, and they're actually pretty small. There's no multi-gigabyte allocates in here, and yet the Riak is still growing and growing and growing. And so this is where we really started to drill into the library.
It's becoming harder and harder for us to blame the application, unfortunately.
Right. I mean, I think at this point I told Voxer, it's like, yeah, I think it's us. It's like, and knowing the road ahead I had to go through this stack into libumem and understand the allocator, and allocators can get really complicated. I mean, it's complicated on purpose. It's very clever. It has, it's multi-threaded aware. It has a per CPU cache. But debugging this to figure it out, and we do have dtrace. So dtrace takes us from it being impossible to possible. I looked at large allocs. These are the ones that were growing the heap. It made no sense because they're only 8 megabytes in size. and then created a whole heap of other tools and looked at memory entropy over time. So actually balancing the mallocs and frees and seeing if they were balanced. And they were, even though the heap was growing, which sounds like fragmentation. We're looking at the code path taken for allocations, successful with unsuccessful. We're looking at allocator internals and so on. And just as this is what my screen looks like when I'm digging into this sort of thing, getting a lot of detail out, getting timestamps out and sizes and arguments and stack traces to really get into the heart of the allocator. And we found out that the allocator was using a allocation algorithm called instant fit, which wasn't working well. It was actually leaking or fragmenting memory and causing the heap to grow, which had been hypothesized earlier, but it seemed very unlikely. We needed the tools to prove it. And so we then had, Robert Mustaki had a version of libumem where we could force a different version of the allocator to fix the issue, best fit, and that solved the problem. Now that was a really interesting problem. That's why we bring it up at Surge, in that this isn't actually the first time I've had an issue with the OS memory allocator. I have had this before, something similar. We've also had issues with libc, where libc libc's malloc is not designed to be multi-threaded scalable, and so that's why we switched to libumem.
And this is, not the only kind of system where we have this. I mean, in these dirty systems that are, they're often event-oriented. If you're building an event-oriented system, memory growth is going to be your inability to keep up with work. So in as much as what you need to do exceeds your ability to do it, you're going to see that blossom out in your memory growth. Memory growth is really critical to understand. In this case, it happened to be due to us, but this issue is interesting because it's basically never the case. Right. Or we assert. What is much more likely is you're going to get application growth up the stack, and in an interpreted environment, you're going to end up with memory that has been semantically leaked. You're no longer using it, but you haven't actually freed it up. You haven't actually eliminated the reference to it. It can't be GC'd. And we had this problem of how do you debug node.js leaks? We're not going to go into this now. We obviously are out of time. But we developed something called find.js objects, thanks to some great work that Dave Pacheco did, presented yesterday. And you can go Google find.js objects to get more details on it. But this allowed us to actually understand the heap in terms of the JavaScript objects. I think we're out of time to talk about CPU scheduling, unfortunately.
That's fast.
That's only 3 minutes fast, right?
Yeah.
Right. So it's like, yeah, but we're just going to go briefly. We'll put these slides online. Right. But with CPUs, I do want to show the heat map here. This is Brendan developed what we call sub-second heat maps, where he's actually looking across the second who is actually scheduled. So if you've got the passage of time in 1 second increments on the x-axis, and the passage of time in sub-second increments going up the y-axis. So if you can visualize that, and you shouldn't have what we have here, where you see these long stretches of one thing running. This was running two little goobers that should have been multiplexed on the CPU. They weren't, and we were seeing this problem where, and this ended up being again, you get the expected, the bad, and the inconceivable for these outliers using the SCED-off CPU probe and dtrace, and we can see that we end up getting pulled off CPU for way too long. And this ended up being a bunch of things. We ended up having a kernel scheduler issue that we needed to go resolve. We actually had just a bug in the kernel where I shouldn't say bug, a performance problem in the kernel, order of n cubed algorithm in the kernel. Actually, order of n squared, only with Redis. Redis can only tickle it because of the strange way it does persistence. But what we ended up with is having to go fix a bunch of issues to go address this. And with issues like, you're always going to have issues like this. You're always going to have issues way down stack. You're going to have CPU scheduling issues. You're going to have networking issues. You're going to have memory issues. And you've got to be able to analyze that full stack to figure it out. And so this is what we've been doing. We ended up with another fair share scheduling issue, a little frowny face there. We can go into that in more detail. One thing I just wanted to just show you is this flame graph that Brendan developed that allowed us to take stack traces when you're running on CPU. And Dave Pacheco developed this unbelievable piece of technology that used the dtrace ustack helper mechanism, developed a node.js ustack helper. I need to keep Dave alive because no one else understands that code. That is brutal code. But it allows us to actually take a stack frame at a time of interest when you're on CPU and look at it in terms of node. Hard to see it down there, but that's actually JavaScript frames. And this flame graph is showing you how much time you're actually spending on CPU. So we can see we're spending a bunch of time in this particular function, which is a JavaScript function. We're getting the actual location and so on in the actual app. So tremendous technology. Voxer's been using this a ton. I love the fact that he sends us these flame graphs. In fact, one problem when you have observability tools like this is people use them. Damn. And we end up on a system that is otherwise happy. Matt will send us email being like, hey, I did a flame graph. Like, what the hell is this? Or I'm looking at this like latency outlier. Like, why I did 3 million IOs and one of them had this outlier. It's like, oh, come on, Matt, Jesus, it's 1 out of 3 million, dude. It's like, no, but seriously, like, why should it take that long? Like, seriously, I don't know. I'll look into it. I'm sorry. So, you know, this is the peril of these tools. You know, in terms of dirt in production, and sorry for the ransom note on one of the bullets there, but what we have learned for these dirty apps is that you've got to understand latency. You've got to understand it from the bottom of the system all the way up. We've added a bunch of stuff to node.js, to SmartOS to allow us to understand it, but I think that's still where we're going. And it's not just Node.js, by the way. I mean, Node, I think people conflate Node with the problems it's being solved for. Node pulls together many different components in the system. You need to understand all of them when you're trying to develop a dirty system. It is not good enough to think that you're going to understand one of these components. And again, it's becoming a cliche, but truly, and I think this is what Surge is all about, we are moving towards full stack engineering, where you need people to understand everything from the instructions that are being executed on the microprocessor all the way up to the interpreted environment, be it Java, Ruby, Python, JavaScript, what have you. We need those of us who can understand that full stack. And that's what this room is all about, as far as I'm concerned. And the good news is that we got a lot of work to do because we got a lot of dirty apps out there. These are exciting apps, but we've got a lot of hard work to actually go make them work. And with that, with our apologies for being a bit over time here, thank you very much.